In this video, we present the production of Portland cement, or OPC. In a previous video, we presented a brief history of this material, and in the next one, we will discuss its hydration. In these videos on OPC, some comparisons are made to natural cement, a late 18th to early 19th century mineral binder that was replaced by OPC, for which further information is provided in two separate videos. Portland cement is produced by burning a mixture of 80% limestone and 20% clay at around 1450 degrees Celsius. Clays are dehydroxylated at about 650 degrees Celsius, while limestone decomposes to calcium oxide and CO2 at around 850 degrees Celsius, depending on the CO2 partial pressure. Note that in cement chemistry, CO2 was originally noted as C with a superscript. For typeset convenience, it is now often noted either C' or C small c. The decomposition of limestone accounts for 60% of CO2 emissions from cement production, the rest coming from the combustion of fuel. Overall, cement production accounts for 6 to 8% of anthropogenic CO2 emissions. In modern cement plants, the decomposition of limestone takes place in a precalciner placed before the kiln. This precalciner is fed with hot air stream coming out of the kiln and heat recovered from the quenched material produced in the kiln, so that heat is very efficiently recovered. Nowadays, clinkering takes place in rotary kilns. They are fed with the hot mix of calcium oxide and clays coming from the pre-calciner. These kilns have a length of around 70 meters and a diameter of about 7 meters. They are the central element of modern cement plants and a key part of making cement production a continuous and highly efficient process. Rotary kilns are heated by a burner placed at their exit so that the temperature gradually rises through the kiln. In the first part, calcium oxide and calcined clays react to produce dicalcium silicate, 2CaO.SiO2, noted C2S in cement chemistry. Its impure form in industrial cement is called belite. At this stage, we additionally have the formation of some amorphous calcium aluminates, similarly to what happens when producing natural cements. As the material moves through the kiln, the temperature rises and two things happen. First, the aluminates form a liquid phase that can be seen as a solvent for high-temperature reactions. Second, a reaction between C2S and additional calcium oxide takes place to form tricalcium silicate, 3CaO.SiO2, or C3S in cement chemistry. This phase is the most important one in Portland cement. Its impure form in industrial cements is called alite. The reaction forming C3S becomes thermodynamically favorable at temperatures above 1250 degrees Celsius. However, higher temperatures are needed for an effective reaction, so that kilns typically aim to achieve a maximum temperature of 1450 degrees Celsius, whereby the rate of C3S formation is enhanced by the aluminate melt that increases the mobility of the reactants. At the kiln exit, clinker contains a lot of C3S, which is thermodynamically stable in the kiln but unstable at ambient temperature. This is why it has to be rapidly cooled or quenched to avoid this tricalcium silicate from decomposing back to dicalcium silicate and calcium oxide. As mentioned for natural cements, the hydration reaction of C2S is very slow, on the order of months. The reaction of C3S is much faster, on the order of hours to days. So Portland cement aims for high amounts of C3S, between 50 and 70% of the clinker mass, with then much lower amounts of C2S. Apart from this, excess free lime or calcium oxide should be avoided. Indeed, its reaction with water forms calcium hydroxide, which, when formed from free lime, can cause expansion and cracking of hardened cementitious materials. So, To ensure their dimensional stability, the amount of free lime must be minimized, keeping it below 1 to 2% of the clinker mass. An important aspect of quenching in modern cement plants is that the heat released in this operation is recycled by sending it to the pre-calciner. This greatly contributes to making modern cement plants thermally highly efficient. After cooling, clinker, together with about 4% gypsum, is ground to a fine powder. These fine enough particles have diameters between 1 and 100 microns. For means of comparison, human hair ranges from about 18 to 180 microns. The ground mix of clinker and gypsum is known as Portland cement, often also called ordinary Portland cement. Portland cement contains 4 phases. 2 are silicates and 2 are aluminates. We already mentioned the silicates C3S and C2S, which we saw are also called A-lite and B-lite, referring to their impure forms found in industrial cements. The aluminate phases are tricalcium aluminate, 3CaO.Al2O3, noted C3A in cement chemistry. There is also a calcium aluminoferrite phase, 4CaO.Al2O3.Fe2O3, noted C4AF in cement chemistry, or better, C2 brackets A, F, as it is a solid solution. C3S represents 50 to 70% of Portland cement and is responsible for most strength and durability. Its reaction with water produces both CSH and CH. The same 2 phases are produced by the hydration of C2S, but at a much slower rate and in different proportions. This, together with an abundance of only 20%, means that C2S is only of secondary importance in Portland cement. Tricalcium aluminate only represents about 5% of the clinker, but is nevertheless very important because it is the most reactive clinker phase. Its reaction is controlled by the gypsum, which prevents it from causing workability loss and/or a delay of the C3S hydration, as explained in a separate video. C4AF, or better C2 brackets A, F, is present in similarly low amounts as C3A. Within the first day, it reacts similarly to C3A, but then becomes much slower. This is why it is not given much consideration here, apart from the fact that it gives the grey color of Portland cement. Somewhat ironically, this grey color is what led Asbdin to call this material Portland cement, while C4AF is not responsible for the strength he praised as being on par with Portland stone. The proportions of these different phases, along with the cement fineness, largely determine cement performance. This is why, in modern cement plants, continuous quality control of composition and fineness play a very important role. This involves measuring the proportion of atoms in the mix using X-ray fluorescence and controlling the specific surface area either by measuring particle size distribution or the Blaine-specific surface area, which is based on measuring the air permeability of a packed bed of cement particles. Additionally, an increasing number of cement plants use X-ray powder diffraction to quantify the phases formed. In conclusion, the manufacturing of Portland cement is a highly optimized and well-controlled process, of which the main challenge today consists in reducing the associated CO2 emissions. Even if we completely move to renewable energy sources, this would only address 40% of the problem. The remaining 60% emissions are related to the calcining of the limestone and may be reduced by substituting part of the clinker by supplementary cementitious materials, referred to as SCMs. These are added during or after the grinding, as discussed in a separate video.